Markus, we cannot hear you. I think you are muted. You should mutate, I think.
Yes.
Yeah.
Now you can hear me. Okay.
Yeah.
Sorry for that. Okay. Thank you very much for the invitation, for the opportunity to talk here. And as you can see here, I will talk about joint work with Peter Bermans, Anna Brekan, Hans Franzen, Gianni Petrella. And this is very recent work from November. And it's my first opportunity to talk about this, to give a research talk about this. And this requires some thought, because usually if the things you're talking about are really, really fresh and you're talking about this for the first time, then usually you make the mistake that you are talking about the lemma you love the most. This one technical lemma you're particularly proud of. And this is something nobody in the audience can understand. So I really had to mentally prepare that I will not tell you about any of the technical details, which I'm maybe proud of because they finally helped me improving this, but I will just give a gentle introduction. I also saw that in the RA seminar, you didn't have that many talks on the geometry of quiver representation. And so I will also give a gentle introduction to these more geometric aspects, and then finally state the result basically without going into the technicalities of the proof. So that's the idea. And so let me in particular start with the why. Why are we doing this? Okay, so here's an overview. So what we will be interested in is representations of finite dimensional algebras of infinite representation type. If you have a finite dimensional algebra of finite representation type, then all the classification is discrete. You have finitely many indecomposables. You have finitely many isomorphism classes of representations per dimension vector. So everything has a discrete classification. But as soon as we leave the world of finite representation type, we have to deal with infinite families of representations. For example, with tame algebras, we have these famous one-parametric families of indecomposables, which we see, for example, for the Kronecker quiver. And if we have wild algebras, then we have parametric families of indecomposables of higher dimensions. And we have to deal with this. We cannot avoid this. We cannot study algebras of infinite representation type only by discrete means. So we have to deal with families of representations. And that is the central notion for today, families of representations. And as an overview over what I would like to explain, we will have the following 4 parts of the talk. So in the first part, I will just give you a formal definition of a family of representations and discuss this definition a little bit and show you ways of constructing families of representations in general. Then in the second part, I will show to you something which is already 30 years old. It was already done in the paper by Alistair King on moduli spaces of representations. But anyway, I will repeat it. Namely, the existence of so-called universal families of representations. Not of all representations, but only of so-called stable representations. I will also recall this definition. And in constructing these so-called universal families, I will also describe the construction of moduli spaces of quiver representations, because these are linked anyway. Yeah. So we have a notion of families of representations, and then I will show you under certain in certain situations you have a universal family. And once you know that such a universal family exists, well, because it's universal, apparently it's very important. So you have to know its properties. And what we will work out today is the homological properties of these universal representations. And so basically everything goes back to a conjecture of Schofield from the early 90s. And we will prove large part of this conjecture of Schofield, basically. And this main result on the homological properties of universal representations will then have actually applications to the geometry of moduli spaces. And these were the applications I was particularly interested in, because I really like to understand the geometry of these moduli spaces. Okay, so that's the overview. That's the plan for this talk. So let me start with a very gentle first step, the definition of families of representations. No, okay. So before we start with that, we have to go through some standard notations on quivers. Okay, so let me also tell you, The first two parts here, the definition of family of representations and the existence of universal families, all this will make sense for arbitrary finite dimensional algebras. But in the whole talk, I will concentrate on representations of quivers without any relations. First of all, because that is essentially the whole story, and the general case follows from this. Also because the main result, which I will tell you, is only in the situation of quivers. And also because I just personally like representations of quivers. Okay, so everything will be just in the language of representations of quivers. And so we have to go through some standard quiver notation. And let me do this first. So first of all, I will always work over the field of complex numbers. Algebraically closed field of characteristic 0 is also fine, but for the geometric purposes, it will be easier to work over the complex ones. Okay. All the time, Q will be a finite acyclic quiver, so that the path algebra is a finite dimensional algebra. And I will always denote the set of vertices by Q0, and I will always write the arrows in the quiver as alpha from I to j. Okay, so then we will look at complex representations of Q, actually finite dimensional representations, and they always consist, let's just repeat this, of a collection of C vector spaces, Vi, for each vertex of the quiver, and C linear maps V alpha from Vi to Vj, for every arrow alpha from I to j in Q. That's the standard definition of a quiver representation. I will repeat this at this point because on the next slide we will generalize this to families, and that's why we need to recall this. Okay, two more ingredients attached to a representation. We have its dimension vector, which is just the collection of dimensions of the vector spaces Vi, and they together form a vector in the free abelian group ZQ0 generated by the vertices. And then we have the Euler form of the quiver. This is the homological Euler form, dimension of hom minus dimension of x1, which explicitly is given by sum over all di ei minus sum over all the arrows di ej. Okay, so that is the standard quiver notation, which I will need in the following, and I'm pretty sure we all agree on this. So then we can come to the definition of a family of quiver representations. A family of representations of Q. And now I denote quiver representations by V, and a family I always denote by the curly V. Yeah. So if something is written curly, then it's always a family. A family of representations indexed by a certain geometric space, namely in our case by a complex algebraic variety, is the following. We take a representation of the quiver, but not a representation in the category of vector spaces, but in the category of vector bundles on X. So a family of representations consists of vector bundles, curly Vi, for all vertices, and vector bundle maps V alpha from Vi to Vj for all arrows. Yeah? So this is word by word the definition of a quiver representation, but we are not representing the quiver in vector spaces, but in vector bundles over a fixed algebraic variety. Yeah? And so from this categorical point of view, this is a quite obvious generalization of the notion of an individual quiver representation. Now, let's discuss this definition a bit and see why this is really conforming with a picture of a family of quiver representations, which we might have in mind. So, discussion. If we are given such a family curly V over a variety X, for every point X in X, we can consider the fibers Vix. Yeah, so we have these vector bundles Vi, and for every point X, we have the fiber Vix. And these vector bundle maps V alpha then induce maps between the fibers. So we have a quiver representation in the ordinary sense on the fibers for every point X in our variety. So we can imagine curly V as a family of representations, namely the family of representations in the fibers, and it is indexed by X. Yeah? So we have X is our base variety, and over X we have a whole family of representations in fibers, which continuously varies with the point in X. It's a continuous family of representations. And this continuity already has some consequences for the representation. Let me just note one consequence, one observation. We observe that if our variety is connected, then the dimension vector is constant along a family. Yeah. So in a family of representations, you always have constant dimension vector if the base is connected. The reason is, well, the dimension vector is just the rank of these vector bundles, but the rank of the fibers, the dimension of the fibers in a vector bundle is constant along the whole space because we have a continuous family. And in the continuous family, we cannot have a sudden jump of the dimension. Yeah? So in particular, we see the dimension vector is always constant along a family as long as the base variety is connected. Okay, so this is one or the other point of view which you can have on families of representations. Either you really imagine a whole set of representations which somehow continuously depends on the base X, or you just say, I represent the quiver in the category of vector bundles. And by the way, how you think about your category of vector bundles, that depends on your taste. I mean, you can view vector bundles really in the elementary sense on a variety. So it's really something which you can trivialize over every open set, or you can also somehow work more in the world of algebraic geometry and view vector bundles as special sheaves, namely as the locally free coherent sheaves of the variety. And what you prefer depends on your point of view, and both points are fine for the purposes of this talk. Okay, so that's the general idea. Now let me come to examples. Let me show you a general construction of vector bundles, of families of representations, where you can really see this aspect that somehow the representation continuously varies with the point in the base variety. So class of examples. A very easy class of examples, if we take an arbitrary base variety X and we take all the vector bundles trivial. Why not? Yeah, we can take the trivial vector bundle, and the trivial vector bundle over X looks like X cross a vector space. That's it. That's a trivial vector bundle. And this looks trivial from the aspect of vector bundles, but still you can build very, very non-trivial families of representations in this way. Namely, a representation, a family of representations not only consists of these vector bundles, VI, which are trivial, but also of these vector bundle maps. And even if the vector bundles themselves are trivial, the vector bundle maps can be highly non-trivial, as I will show you now. We can have the linear maps depending on X. Let's look at this. Namely, we should have a map VL, curly V alpha. It should be a map from the trivial vector bundle X cross VI to the bundle X cross VJ, if alpha is an arrow from I to J. So let's write down a formula for this map. So V alpha of X comma VI, well, for this to be a map of vector bundles, we should stay in the same fiber. So V alpha should map this X to X. And we send VI to, here's a typo, this should be a VI, sorry, F alpha of X of VI. So we can have this map V alpha depending on the point X. So we can take continuous maps or algebraic maps from our base variety X to the Hom space, to this vector space. And for every such algebraic map, polynomial map, you can have this family. Yeah. So even if the vector bundles are trivial, you can have highly non-trivial and many, many families of quiver representations in this way. Okay, so that's a very general construction. And this shows that there are many, many families of quiver representations. And also examples you can keep in mind, well, whenever you try to classify, say you classify indecomposable representations, then for some dimension vectors, for a non-Dynkin quiver, the indecomposables appear in continuous families, and you cannot avoid this. These are other standard examples of such families. All right. Okay. Now, in principle, I would like to tell you about the so-called universal families, but before I can do so, I have to tell you a bit about stability. So let's somehow stop this discussion of families for a minute and discuss the notion of stability on the next slide. Okay, so to define stability of quiver representations, that's not an absolute notion. It always depends on a stability function, theta. So now we fix a linear function theta, okay, 0, from the Grothendieck group of the path algebra, which is nothing else, because the quiver is acyclic, than the free abelian group generated by the vertices to z. So it's just a functional on dimension vectors. A representation V is then called theta stable if the following condition holds. First of all, theta applied to the representation itself is 0, and theta applied to every non-zero proper subrepresentation is strictly less than 0. So stability is a condition on the lattice on the set of subrepresentations of representation. Yeah, so we want subrepresentations only of certain dimension vectors, and which subrepresentations are allowed and which are not allowed depends on the choice of this theta, which from the very beginning is completely arbitrary. The only problem is that if you make a wrong choice for theta, then usually you don't have any stable representations at all. But let's assume that for some reason we made a good choice of this theta and we define this notion of stability. Then one important point is that stable representations are automatically Schurian. So they have trivial endomorphism. And this is a very simple Schur-Slemmer type argument, but I really like this argument, so I will just give you the proof or remind you of the proof. So, namely, let's prove that a stable representation is automatically Schurian. So let us suppose that phi is an endomorphism of V, which is non-zero and non-invertible. Okay, so if it is non-zero and non-invertible, then both the kernel and the image are non-zero proper subrepresentations. The kernel is a proper subrepresentation because phi is non-zero, and it's non-zero because phi is non-invertible, so it's not injective. And the image is non-zero because phi is non-zero, and the image is proper because, well, phi is not surjective because it's non-invertible. So kernel and image are non-zero proper subrepresentations to which we can apply this numerical condition. And then we have the following chain of inequalities. So first of all, since the image is a proper subrepresentation, theta of the image is strictly less than 0. Okay. The image is isomorphic to V divided by the kernel. So instead of writing theta of image, I can write theta of V divided by the kernel. Now, theta is a functional on the Grothendieck group. So theta of this quotient representation is theta of V minus theta of the kernel. Theta of V is 0 by assumption. And since the kernel is non-zero proper, theta of the kernel is strictly less than 0. So here we find 0 minus something strictly less than 0, so it's strictly bigger than 0. So at the end, we have 0 is strictly bigger than 0, which is a contradiction. So we have a contradiction to our choice of phi being non-zero and non-invertible. So that means every endomorphism of V is either 0 or already invertible. So the endomorphism ring is a division algebra over C. It's finite dimensional because V is finite dimensional, so it has to be C itself since C is algebraically closed. So this proves that all stable representations are automatically Schurian. But not every Schurian representation is theta stable for some theta. This can be seen even for dimension vector 2, 3 for a 3-arrow Kronecker quiver. It's not completely trivial. You really have to think about an example, but it is in general, the class of stable representations is much more special than the class of Schurian representations. This we should keep in mind for for the discussion of universal families later. Okay, so that was a brief digression into stability. And now we go back to the topic of families. And for this, let me again come back to this slide. That was the definition of families. So, sorry. Here we go. Family is a representation of the quiver in vector bundles, or we can view it as a continuously varying family of representations. And we have seen that there is a huge supply of such families, even if your vector bundles are trivial. Okay, so now let me tell you about the universal family, which is absolutely amazing. And you wouldn't have guessed it maybe that this exists. And so that's a theorem of King in his 1994 paper on moduli spaces of pure representations. We fix a dimension vector for which we need a special assumption. It has to be indivisible. So indivisible in the sense that the greatest common divisor of di of all the entries is 1. That is important. That is definitely a necessary condition for what follows. In this case, there exists a family of representations which is universal. So there is a universal family U over MD, and I will tell you later what MD is. It's the so-called moduli space. It's a family consisting completely of theta stable representations, and it's universal in the following sense. Whenever you have any family over any variety X, so every family V over every variety X, consisting of stable representations of dimension vector D, you automatically get a unique map F from X to MD such that V arises as the pullback of U. So here's a diagram. So here sits this universal family, U over MD. And it's universal in the sense that it has a universal property, namely, whenever you have a family coming around V over X, this family automatically gives you a map from X to MD, such that the V actually arises as the pullback of this vector bundle to this space. And if you think about it, this is amazing. So first of all, it has various restrictions for this universal family MD. So for example, just think about the following example. Your family V over X, it could be a single representation. Every single representation is a family over a point, yeah? Obviously. So whenever you have a single representation over a point, a single stable representation, this family arises as the pullback. So that means, first of all, every stable representation has to appear as some fiber in this family. Yeah, so it has to appear as some fiber in this family because, well, this representation has to arise as pull back to a point. And pull back to a point just means take the fiber. Yeah, so every stable representation is in here. And because of uniqueness, every stable representation appears as a fiber once in its isomorphism class. And the universality is just really amazing. I mean, these families V over X, they can be arbitrarily complicated. And I've shown you this very general construction of families, even on trivial vector bundles. But all these possible families are captured by this one universal family for each indivisible dimension vector. And this is really surprising that this exists. But let me also mention that this result is optimal if you look at families of all representations, or of all indecomposable representations, or even of all Schurian representations, then such universal families usually don't exist. It's not at all trivial to construct counterexamples. One really has to think about what such a family means, but there are known counterexamples to all of this. Yeah, so even families of Schurian representations cannot be captured by universal families. So you really need this stability. It's absolutely crucial for the existence of these universal families. Okay, so the logic of the talk up to now is the following. If we are an infinite representation type, we have to deal with infinite families, continuously varying families of representations. Okay, fine. And now we have a universality result, at least for indivisible dimension vector, and at least for stable representations, we can capture all these continuous families in one universal family. So this universal family, it must be something great. So we really have to know it and we have to study it. Okay, so and that's the next part of the talk. I will now first show you how this universal family is constructed, and then we will discuss its properties. And the construction is intimately related to the construction of moduli spaces of quiver representations, and that's why we have to go through the definition of moduli spaces. And once we have defined the moduli spaces, we somehow get this universal family more or less for free. Okay, construction of universal families. Okay, so first of all, we are given a fixed dimension vector, and this is wrong. This fixed C vector space is VI of dimension VI. I've reread these slides like 10 times, but I haven't noticed this. This should read vector space is VI of dimension TI. Yeah, we have a fixed dimension vector. So we fix the vector spaces of correct dimension, and we look at the variety of representations, RD of Q, which is just the direct sum over all arrows alpha, Hom from VI to VJ. So what does this mean? Well, this, first of all, is just an affine space. It's a direct sum of vector spaces. And a point in this space is a collection of these maps V alpha, which I will abbreviate by V. And such a point is therefore nothing else than a representation of Q on the fixed spaces VI. Yeah? So the datum of a representation consists of fixing the vector spaces, and this I've done in advance because of fixing the dimension vector, and then prescribing the maps between the vector spaces, and the choice of all these maps is now encoded as a point in the space. Yeah, so a point in the space is just a representation of Q on the spaces VI. In particular, it's a representation of the fixed dimension vector D. We have a group acting on the space, namely it's the base change group. We take the group of automorphisms of each vector space, so the product over all I, GLVI, and it acts on this variety by the usual base change action. So like an indexed variant of the adjoint action. GI acts on V alpha by taking GJ, V alpha, GI inverse, if alpha is a map from I to J. Okay, so by definition of a quiver representation, of quiver representations, the orbits for this action are the isomorphism classes of representations of dimension vector D. Yeah, because two representations are isomorphic if and only if they are related by such automorphisms G in this way. Aha. So isomorphism classes of representations are nothing else than orbit of a group in a certain affine space. Let's come to the stable representations. The theta stable representations, regardless of what theta is, they form an open, a Zariski open subset of RD, which I call RD theta ST of Q. Most of the time, this subset will be empty, yeah, because as I said, it's a subtlety which theta to take, and usually it's difficult to check whether for a given dimension vector and a given theta you have a stable representation at all. But let's just assume we have some knowledge about the situation and we can make a choice where we know that there is a stable representation. Then the set of stable representations is open. It is Zariski open, and a Zariski open subset is very large. So it is in particular already a dense subset. Yeah, so almost all representations are stable if there is a stable representation at all. Okay. Then what we are interested in is the orbit space. So what is this orbit space? So I write here RDST divided by GD. And this should be just the set of all orbits. And what is this set of orbits? Well, the set of GD orbits in RDST is the set of isomorphism classes of stable representations. Yeah? So this here is a set indexing the isomorphism classes of stable representations. And we call this MD, or more precisely MD theta ST of Q. And this is not only a set, but in fact, and this is a non-trivial fact from algebraic geometry, it admits a unique structure of a complex algebraic variety, such that the canonical map from there to the set of orbits is an algebraic map. Okay, so I will repeat this last thing on the next slide and then continue. Okay, so here it is. The orbit space, set of stable representations modulo structure group, which is a space or a set parameterizing isomorphism classes of theta stable representations. This admits a structure of a complex algebraic variety. Aha. So it qualifies as the base variety for a family. Well, first of all, this space MD, that is called the moduli space of stable representations, or more precisely, the moduli space of isomorphism classes of theta stable representations of Q of dimension D. Okay, that was a very quick way to introduce these moduli spaces. And now let me construct a family over MD, yeah, this universal family. We go back to this representation variety, RD of Q. Let me quickly jump back to the last slide. RD of Q is nothing else than the direct sum of all these Hom spaces, yeah? So a point in RDQ is just a collection of the linear maps which you can write at the arrows of the quiver. And this carries a tautological family, namely, continuing on this example before, we take the vector bundle over RD of Q to be trivial. Yeah, so the vector bundle is just base space times the vector space VI. Sorry for all these emails which I get. And okay, and here is the choice of map. The map V alpha maps VI to V alpha of VI. And this is why this family is called tautological. So in defining the vector bundle map V alpha, you take the curly V alpha, you take the V alpha, which you take from the V, from the point in this representation space. Yeah. So, I mean, in the way I write this down, it looks absolutely tautological. And in fact, it is. And that is why this is called the tautological family. And now the amazing thing is, if your dimension vector is indivisible, and only if you can put a GD action on this tautological family VI so that it descends to the quotient MD. Yeah, so you have to descend modulo a group action, and then you get vector bundles, which are no longer trivial. You get vector bundles UI over MD, and these vector bundles come with vector bundle maps U alpha, and they form this amazing universal family. So that ends the construction. And let me quickly go back to this main defining property of the universal representation, which we have now constructed. Here we go. The universal representation is a representation of the quiver in vector bundles over this moduli space of stable representations, such that any family arises by pullback from this universal. Okay. That was detailing the construction of this family, and now we come to the main result. So let me briefly mention, up to this point, everything could have been done not only for representations of a quiver, but also for representations of a quiver with relations. So for arbitrary finite dimensional algebras up to Morita equivalence. I could do all this for arbitrary algebras. But usually these moduli spaces which appear there are extremely badly behaved, and there's no way to, or almost no way to study them. Yeah? And so it all makes sense for arbitrary representations, arbitrary algebras, but it is only interesting to study this at the moment, at least for quivers. Okay, so main result. Now we have this universal families U over MD. It's the universal family of theta stable representations of dimension vector D over this moduli space of stable representations of dimension vector D. Because of its universality, it's definitely something we should study. We should know properties of this universal family, and particularly we should know homological properties. Now, the first thing we have to ask ourselves is homological properties in what sense? I mean, as an element of which category? And so first we will now study homological properties of these universal families as vector bundles. Yeah. So before I can now formulate the main result, we have to quickly work through one technical condition, which appears frequently in this study of vector bundles on moduli spaces, and we cannot avoid this. We call a dimension vector theta strongly amply stable, sorry for the clumsy notation, terminology, if the following holds: for every proper decomposition of the dimension vector into E plus F, for which theta of E is bigger than theta of F, we should have that the Euler form of EF is less than or equal -2. Actually, it turns out that the only value you have to avoid is -1. Yeah, so there are certain bad things which might happen in codimension 1 which you have to avoid. But first of all, this condition is important because it implies that the non-stable locus in RD of Q has codimension at least 2. The non-stable locus is the complement of the stable locus. I told you before, let's quickly go back. I told you before that the stable locus in the representation variety is always Zariski open. So most representations are stable, but the complement is a closed subset, and we want this Zariski closed subset to be rather small. It should be of codimension at least 2. And for this condition to hold, we need this numerical condition here. This numerical condition is difficult to verify, even in particular cases, but just very recently, just last week, we found sufficient conditions for this strongly ample stable, which imply in particular that it is always fulfilled for quivers with at most 3 vertices. Yeah, so there are lots and lots of examples of this technical condition. If your quiver has 1, 2, or 3 vertices, it is always fulfilled. Okay, but it is really a mysterious condition, to be honest. Well, anyway, we have to assume it for our proofs, and now comes the theorem. Suppose that our dimension vector is not only indivisible, like it was before, for the existence of this universal family, but now also assume that it fulfills this genericity condition, this strong ample stability. Then, in the category of vector bundles on the moduli space, we consider the bundle direct sum of UI. So these are the UI, these are these bundles in the universal family, these are the bundles constituting the quiver representations. So I'm only considering this bundle. So what I'm ignoring in this theorem is these bundle maps U alpha, yeah, which are part of the representation of the quiver and vector bundles. This will come later. And at the moment I will ignore them, I will just take this bundle. But as I told you, these bundles UI, these universal bundles, they're definitely not trivial in general at all. So there are some mysterious vector bundles. So what are the properties? Here are the properties. They satisfy the endomorphism ring as vector bundles of this direct sum U is the path algebra of the quiver, and all higher x between these vector bundles U vanish. Yeah, so these are homological properties as vector bundles. And what does it mean? Well, it means in particular that U is a partial tilting bundle on the moduli space. And this is apparently a conjecture of Schofield from the early 90s. You cannot find it in any of Schofield's papers, but it is mentioned explicitly as a conjecture of Schofield in papers of Hille and Altmann-Hille from the early or mid-90s. And this was known before by a theorem of Altmann and Hille for the so-called thin moduli spaces. So it was known before in the case when the entries of the dimension vector are 1, always 1. And it was known for special moduli spaces for like quiver flag spaces by work of Alistair Crowe. But so this is a very general thing. What we only need is this slight genericity assumption of strong ample stability. And then this direct sum of the universal bundles, just as a vector bundle, is partial tilting. It is far, far away from tilting, I should definitely say. So nobody knows how tilting bundles on moduli spaces might look, but at least we know that this is a partial tilting bundle, and the endomorphism ring is the path algebra of the quiver. So we can reconstruct the path algebra of the quiver from these universal bundles, which is maybe not a surprise because they are, well, universal. Okay, so that's the main result, and I will not tell you anything about the proof of this because, well, this is the content of one of the two papers, and this is the content of the other of the two papers, which I wrote on the title screen. And both formulas require completely independent techniques. So this here requires an application of so-called Telemann quantization. So Telemann quantization is a general technique for proving vanishing results for vector bundles on quotient varieties. And we have to adapt this technique to have this cohomology vanishing here. And this computation of the endomorphism ring, that requires somewhat an ad hoc trick, a so-called double framing construction. And using this double framing construction, we can reduce everything to the study of line bundles. I mean, these UI usually have higher rank, but we can so reduce them to rank 1. And then we can make a detailed consideration of line bundles, and then we can actually compute this. So technically, these are two separate theorems, although they fit together nicely, and they require completely different techniques. Okay, so that was the main result. And what is very interesting about this is the applications. And in particular, if you read partial tilting, then of course you might think, well, what about applying a tilting functor? And let's first do this, and let's look at something like a tilting functor, and let's find out one of the consequences. Okay, so U is a bundle this on the moduli space, this direct sum of the UI. But as I said before, it has much more structure. We also have these maps U alpha. Yeah. So if you have a bundle on a vector space, you can view it as a sheaf. Namely, it's a locally free OMD module. So OMD is the structure sheaf of this variety, and you consider coherent sheaves over on this variety. So a locally free OMD module. It is even a OMDQ module. So what is this? This is something like the path algebra. So it's the sheaf of path algebras, the path sheaf of algebras on the space. Yeah. So imagine like taking the path algebra, but as your coefficient ring, you don't take C, the complex numbers, but you take this the structure sheaf of the variety. And this OMDQ module structure, that requires really these vector bundle maps U alpha, which constitute part of the family. Okay, and then we can write down a tilting functor. Namely, we can take a functor from the bounded derived category of representations of the path algebra to the bounded derived category of coherent sheaves on the moduli space. And this functor is given as follows. It's the derived of the sheaf hom from U to tensor product with OMD. So let's see whether this makes sense. So in this functor, you can plug in a complex of representations of your quiver. So let's just assume a representation of the quiver. You plug in a representation of the quiver. Tensoring it to OMD gives it then a structure of an OMDQ module. U, the universal bundle, is also an OMDQ module, and then we take the hom between these two OMDQ modules, but we take the sheafy hom, so it's still a sheaf, and we take the derived functor of that. And in this way, we get a complex of sheaves on MD. Yeah, and this functor, so that's why this functor makes sense, and it really looks like, well, tilting via U. This functor is fully phasing. That's the consequence of the fact of U being partial tilting. Yeah. So we see that in the derived category of coherent sheaves of MD, as a very, very special subcategory, we find the whole derived category of representations of the quiver. And this is again somehow morally confirming the universalities of these bundles U. Yeah, they are so universal that on the bundles of that in sheaves over the moduli spaces, we find the whole derived category of the quiver. Okay, that's the first corollary and an important thing to observe about the geometry of these spaces. And finally, yeah, I have 4 minutes left. That fits perfectly. Let's briefly consider the tangent bundle of the moduli space. The tangent bundle of the moduli space fits into a canonical 4-term sequence. And let me write down the sequence. So here's a sequence of vector bundle of sheaves on MD, on the moduli space. So it's 0, structure sheaf, direct sum of UI check tensor UI. These are the universal bundles. Direct sum along all arrows, UI check tensor UJ, and then T, and then 0. This is a map of bundles. If you go back to your conventional representations, then you will recognize this as the canonical 4-term sequence, which computes Hom and Ext of quiver representations, right? I mean, you usually, for quiver representations, you have a 4-term sequence where here you have the Hom between quiver representations, here you have the Ext between quiver representations, and here you have 2 terms which you can easily compute. This is the simple way of proving that the Euler form is the homological Euler form of the quiver. Yeah? And this standard 4-term sequence for quiver representations has an analog for quiver representations in vector bundles, where on the left-hand side, instead of Hom, you have the O, the structure sheaf, and instead of Ext1, you have the tangent bundle. Okay. Now, about the 2 middle terms, we have lots of homological information. We have all this Ext vanishing here. Yeah. And so playing around with this 4-term exact sequence should give us some homological properties of T. And indeed, corollary is that the 0th cohomology of the tangent bundle is the first Hochschild homology of the path algebra, and first cohomology of the tangent bundle is second Hochschild homology of the path algebra, which is 0. And by the way, all higher cohomology of the tangent bundle is 0 anyway. Yeah. So we have this slightly strange but standard shift in cohomological degree, but 0th cohomology of tangent is HH1, first cohomology of tangent is HH2. Yeah, okay, so this looks quite nice, but it has a dramatic consequence, namely this property here, the vanishing of first cohomology of the tangent space, is very important and very, very special about algebraic varieties. Namely, the first cohomology of the tangent sheaf of a variety parameterizes its infinitesimal deformations. Yeah, as every first cohomology does. First cohomology is always something parameterizing infinitesimal deformations. So that means the moduli spaces of stable representations, they have no infinitesimal deformations. They are rigid objects. And together with Alistair King, when I talked about this as a conjecture today, 1 year ago in Oxford at Alistair King's 60th birthday conference, we came up with the following formulation for this result. Quiver moduli have no moduli. So quiver moduli are varieties which do not admit any infinitesimal deformations. So they, for themselves, have no moduli. Quiver moduli have no moduli. And I think that's a very nice slogan to actually end the talk and say thank you for your attention. Thank you very much.
Thank you very much, Markus, for your very nice talk.
Sorry?
Thank you for your very nice talk.
Thank you.
Are there any questions, comments? Maybe I start with a small question. Your moduli is your bundle. Sorry, your bundle is a partial tilting,
Right.
and can be completed to a tilting.
There is apparently a conjecture of Schofield how to complete it to a tilting bundle. That's part of Schofield's conjecture, but I don't know the details actually. Yeah, but yes, there is more to Schofield's conjecture. So it should be somewhere in the papers of Hiller and Altmann-Hiller. There should be a precise formulation how to complete this this partial tilting bundle to a tilting. I'm not very optimistic about that because there are, well, very simple examples of these moduli spaces are projective spaces or Grassmannians. Yeah. So for example, I mean, for an M-arrow Reineke quiver, you can easily get Grassmannians as these moduli spaces. And for Grassmannians, tilting bundles are known by work of Kapranov from around 1990. And you need many, many more bundles than just these UI. Yeah, you need to apply Schur functors to these bundles UI, various Schur functors to get a tilting bundle over that. Yeah, so I would say you should read this, that U is a partial tilting bundle on MD, really as a property of U, and the U is only a very, very small part of a huge tilting bundle, if it exists, according to this conjecture. Yeah.
Yeah. Are there any more questions, comments?
So just one comment from me. So everything up to this main result, everything up to here in the talk, you can also just have a look at the paper of Alistair King from 1994. It's all in there. Yeah. So that was basically everything about the paper of King, and only from here about these main results. That's about the new paper.
Are there any more questions or comments? Can't see any other question. Thank you again, Markus, for your
Thank you very much for your attention. Thank you. All right, so let me